Another 2 minutes, we'll start. Okay, I hope last class I sent that one, the query, whatever you are making regarding that synchronization with.
Yes, sir. I found another solution. I made. I sent it to you.
Oh, I'll check. Then tomorrow
Okay,
I'll discuss that.
Okay.
So today we'll start the deadlock. At least we'll finish whatever.
The syllabus is up to deadlock for midsem.
Midsem deadlocks only first part, not whole. Okay. So that will start because it is a simple part. If any question comes directly, you can answer. No difficulties will be here. Okay. Yes. So we'll start with the topic called as deadlock. We have gone through the different scenarios of the deadlock, but if you can just once again look over those things. We studied one kind of deadlock, like we need experience and we need for job. So the experience needs job, and if you get the job, then only you can go for the experience. So it is somehow a deadlock scenario, because without job I cannot get an experience, without experience I cannot get the job. So this scenario makes it is deadlock. If you can go technically, let's take, I have a semaphore, that is, let's take P and Q, or M and N, and both will be initialized to 1. So M is initialized to 1, N is also initialized to 1. Then if you can write a code for the process P1 and P2, let's take the process P1's code is P of M and P of N, and then the critical section. Then we'll go for this V of M, or you can V of M, or you can go for V of N. And similarly here we'll go for P of N and P of M and critical section. And here it is a V of N and V of M. If you write on this code, so this basically also creates a deadlock scenario. The reason of the deadlock is that if first P1 enters and here the context switching is happening, and P2 enters and here the context switching is happening. And what happens? This both of them will be goes to 0. Yes or no? After it will go to 0, neither n here the P1 gets the n to be 1, nor the P2 gets the m to be 1, because this P1 is requesting for n, which is occupied by this fellow, and this P2 is requesting for m, which is occupied by this fellow. Yes or no? Because if you can go for this, the P1 is somehow holding this m's value, because he has made come here, means he is holding it, which is demanded by P2. Yes or no? Because P2 is requesting for m, and which is held by P1. In the same manner, if you can go for the n is another semaphore variable, or it is a resource, here this P1 is requesting for this n, whereas this is held by P2. Is it correct? By looking into this, is it okay? What I told, if P1 and P2 are the two processes, here P1 has already made the m from 1 to 0. So he has hold this m. And here the P2 is requesting when the m should be 1. So he is requesting. And as for the n is concerned, this P2 hold this n, because this P2 has come here, means he has changed this n 1 to 0. So he has hold it. And this P1 is requesting for the same n, which is held by this. And if you can look into it, it makes a cycle. So this whole thing makes one cycle. Since there is a cycle exists, that's why here there is a deadlock. So what the deadlock basically says, as per the definition is concerned, so that you can understand clearly, a set of processes. Remember this is very important. The set of processes are said to be in deadlock if every process belongs to this set. Belongs to this set, holds a resource, and waiting for another resource which is currently held by other process, belongs to this same set. So what is saying? Very important. The set of processes means when a deadlock occurs, you don't think that everybody inside the computer system will be gets deadlock. No, few of the processes will be in the deadlock scenario, and that those processes are in a set, and those processes are said to be deadlock if you can consider here the set S consists of P1 and P2 is the set. Both the processes are said to be in deadlock if every process, consider P1 and P2, everybody is holding a resource and waiting for another resource which is held by another process belongs to the same set. Then only it is coming into deadlock will become. Means here this P1 holds this n, requesting for n, and same n is held by P2 and requesting for m, which is held by P1. So this scenario makes you the deadlock. Means neither you can leave this nor you can get it. So that situation makes you become deadlock. So another case you can also consider, if there are many resources are present, the P1 is requesting for R1 resource, R1 is held by P2, P2 is requesting for R3, R2, R2 is held by P3, P3 is requesting for R4 and R4 or R3, and this R3 is held by this P1. If you can say this direction will make a request, this is become a request and this is become hold, means this R1 and P2 is holding and P1 and R1 is become requesting. So if you can consider like this, every process, now here the set is P1, P2, P3, three processes are in deadlock because everybody is holding. P1 is holding R3, requesting for R1, and which is requesting that particular resource is held by somebody, that is P2, which is belongs to the same set. If it is outside of the set, then there is no kind of deadlock. So if this scenario comes and in deadlock, there must be a circular or cycle kind of things definitely exist. Without a cycle, you cannot think of there is a deadlock. And the whole thing will be studied with respect to a graph. If you can think about it is a graph, these are the basically nodes, and these nodes are connected with a directed edge, and in this graph there is a cycle exist. If there is a cycle exist, then there is a possibility of deadlock. If there is no cycle exist, there is no question of a deadlock comes into picture. Very important point. Again, I'm saying if the cycle exists, if a cycle exists, then there may be a deadlock. Maybe a deadlock. If no cycle exists, then there is no deadlock. Directly you can say that there is no deadlock. Now here you have a doubt that why you have written maybe. Why not directly say that it is a deadlock? After a few minutes we are going to discuss. I told cycle exists means there will be a maybe a deadlock. If cycle does not exist, guaranteed there is no deadlock. Okay, then how you can identify that a deadlock has occurred and what is the condition for the deadlock? So let's see a scenario for the conditions for the deadlock. Conditions for deadlock. So basically there are four conditions. So first condition is called as the mutual exclusion. The second one is called as hold and wait. And third one is called as no preemption. And the last one is called as a circular wait. I'll discuss each one of them individually, but what is saying, if these four conditions satisfy, these four conditions are satisfied, then only there is a deadlock.
Sir, and that yes, sir.
Yes, if any one of the condition is violating, not satisfied, means you can directly say that it is not. Means all four conditions, not I have written wrong. If all these four conditions satisfied, if this is not satisfied, there is no deadlock. If this is not satisfied, there is no deadlock. So how they are related and what is the importance of each one of them? Let's discuss. So what is a mutual exclusion? Everybody knows. Anybody please answer. What is the mutual exclusion basically says?
At a time only one process can access the critical section code.
Means the resources are mutually exclusive. Are mutually exclusive. Everybody knows what is mutually exclusive. Mutual exclusion means only one process, as somebody told, will be hold it. Other processes cannot share these resources at a time. So it indicates that, means if I say P1 and P2 are the two processes and R1 and R2 are another resources. If P1 is requesting, R1 is holding, P2 is requested, and this is this, then it is a cycle. Just look into it. Suppose P1 is requesting for R1 resource, that R1 is held by P2. P2 is requesting for R2 resource, that is now currently held by P1. If this is the scenario, think that it is the scenario, then what happens? Which is mutually exclusive? The resources are mutually exclusive. Means if R2 is not mutually exclusive, there is no question of deadlock. Can anybody tell me? If R2 or R1 is not mutually exclusive, then there is no question of deadlock. Can anybody here answer? Why?
Sir,
Yes, sir, because no restriction is there. P1
Very
and
nice.
P2 can
Very
go
nice.
there.
Yes. So somebody told, everybody knows this. It's not like that one person knows only. So it says that this R1, if it is not mutually exclusive, like I tell that it is a kind of resources which can be used by all the processes at a time. So what is the question of hiding? There is no question of hiding. Like I tell, there is a file and the resources are purpose for the reading purpose. If the resources are meant for the reading purpose and there is a file, do you think that is there any issue comes into picture? No issue, because everybody can read this file at a time. Then what is the issue? If there is a resources like printer is mutually exclusive, because I cannot use this printer 2 persons at a time. If 2 persons at a time, what happens? In a single page, half of the document from the first process, another half from the second process. Nobody will like these things. Means all the resources considered here to be mutually exclusive. If something is not mutually exclusive, let's take R1 is mutually exclusive, R2 not, then what happens here? When P2 is requesting for the R2, he can immediately get it. And if he will immediately get it, is there any cycle exist? Let's take, he will get this R2 resource. Then what happens? This is deleted. If it is deleted, then what is the current edges? This is one edge. This is another edge, this is another edge, and this is another edge. Is there any cycle made? No cycle. Why? Because it is going like this, here it is not coming. Means there is no deadlock. Because of this R2 is now used by P1 and P2 simultaneously, which is not allowed. Means every resources belongs to this particular system to be to be in mutual exclusion. Then only there is a possibility of deadlock. If some of the resources are not in mutual exclusive, then you cannot say that it is a deadlock. Then hold and wait. What is the hold and wait says? Means every process must hold a resource and also waits for another resource. Why it is happening? If you can consider like this, the same example, if you can look into it, 1 minute. Nice. If you consider like this, if P1 is requesting for R1 resource, and this R1 is currently held by P2 resource, and R2 is currently held by P1, is there any deadlock? No question. Why? Because P1 is holding R1, requesting R1 and holding this R2. At the same time, P2 is holding R1, but P2 is not requesting. Means this P1 is hold and wait, but this is only hold. If it is only hold, what happens? He cannot execute at this stage because he could not get this R1. Then what he does? P2 is executing R1 because P2 does not demand anything. Once the P2 completes his R1's work, he has to release it. The moment he will release it, then R1 will be received by the P1, and already this P1 is holding this R2. Since R1 and R2 both will be available to this P1, they can do it. Then what happens here? Here it is saying every process must be in hold and wait, because without hold and wait for every process, there is no question of cycle. एक तो edge होगा तभी तो जाके cycle बनेगा ना, because if he is only holding, and there is no requesting. So this edge is not there. If this edge is not there, cycle cannot be there. And as I told, without a cycle, there is no question of deadlock. So that is called as a hold and wait. The same time, no preemption. No preemption. Preemption means what? Forcibly taken away the resources from somebody. But he is saying no preemption is allowed. Means nobody can do any gundagardi there. Means if I am making a request, he is like this, and he is requesting for this, then it is in deadlock. Everybody is holding, waiting. But let's take this rule is not applied. Means there is a preemption. There is a preemption means since P2 is demanding for R2 and currently R2 is held by the P1, if this resource is non-preemptive, then what happens? This P2 forcibly taken this resource, use it, and then release it. But he is saying every resource is present in this system, which is saying that it is in deadlock, those resources cannot be preempted. Means unless until P1 voluntarily release this R2 resources, nobody can access this R2 resources. The reason? Because R2 is currently held by P1, and P1's responsibility is to, the moment this work gets over, he has to release it. Okay, so that's why it is called as a no preemption. And at the same time, the no preemption also says that there must, after no preemption, there must be circular wait. The circular wait, already we have discussed. Everybody, a PI is requesting for RI. RI is held by this P2. P2 is requesting for R2, like this it is coming, and it makes a circular wait. Means P1 is requesting for R1, and last R3, which is requested by P3, it is held by the P1. And this whole thing makes a circular wait. So without circular wait also, this cannot be possible. So that's why if all these four conditions occur, then only there is a chances of deadlock, otherwise it cannot. Now, any questions regarding this? Then I'll go further. Is there any question? Is it understood? Very simple. Mutual exclusion, hold and wait, no preemption, and circular wait. All four conditions should occur, then only there is a question of deadlock. Otherwise not. If any one of them is not possible, then you cannot do it. Now the question comes, how can you identify that a system is in deadlock? Okay, because once you are inside the system, means your program is inside the system, how your program can identify this system is in deadlock or not? Yes. So next question comes, how to identify the deadlock? Yes. So one solution, we'll later see the solutions, other solution. The most important solution is through resource allocation graph. Allocation graph means he's saying with the help of a resource allocation graph, we can identify that whether the system is in deadlock or not. Then what the system allocation graph says that? It is a graph. Since a graph, it must have a vertices and edges. Then what is V here? This V is basically the, you can say the processes and resources. Yes, all the processes and the resources will be considered as the vertex. Then what is the edge? The edges are basically of two types. One is called as the request edge, and another one is called as the assigned edge. Okay, so there are two kinds of vertices and there are two kinds of edges. So let's look into first one. So how the resource allocation graph look like? Let's take I have two processes, P1 and P2. Let's take I have also two resources, that is R1 and R2. Then what happens here? If P1 is requesting, R1 is held by him, he is requesting and he is held by him. Means what? This P1, P2 are the processes which are the vertex, and resources are also vertices. R1 and R2 are also vertices. Since all four are become vertices, then what is the edges? The edges are request edge. So what is the request edge? The request edge is from the process to resource. Means Pi towards Rj, if the direction will be there, means Pi is made a request for Rj. Currently, he has not held it. What is the assignates? The assignates is if Pi is holding Rj towards this, then it is called as the assignates. Clear? This is called as the Rj is the resource currently held by Pi, then it is assigned. If Pi is requesting for Rj, then it is called as the request edge. So by considering this request and assignates, here you can quickly say, sir, this is a request edge, this is a request edge, this is assigned edge. Yes or no? P2 is holding R1. This is a request edge and this is assigned edge. And in this case, this is called as resource allocation graph. Okay? Allocation graph. And what it means, this resource allocation graph, through this resource allocation graph, we can identify whether there is a deadlock in the system or not. Yes. So how will you identify? There are two rules he saying. If there exists a cycle, in the graph, then there may be a deadlock. The same thing already I explained to all of you. So what it basically says? It basically says that if there exists a cycle, then only there may be a deadlock. If not, then so most important thing, this may be a deadlock and exist a cycle. And if you can look into it, there exists a cycle, so there may be a deadlock. But in this case, there is a deadlock. Yes, why? Because this cycle exists. Neither he is leaving this R2 nor he is getting this R1. Because the same R1 is held by P2 and this. Then the question comes very simple. So in which scenario we can say there exists a cycle but there is no deadlock? In this case, I told here there is a cycle exists and there is no deadlock. But in some scenario, you can say there exists a cycle but there may not be a deadlock. Then what is the scenario? Probably you understood now. How can you identify the deadlock? First, you have to draw a resource allocation graph. Inside the resource allocation graph, identify whether there exists a cycle or not. If there is a cycle, then you can think about whether there is a chances of deadlock or not. If there is no cycle, they guaranteed there is no deadlock. Okay. Now let's see a scenario where the cycle exists but there is no deadlock. Okay, so this scenario is given in your book. You can find this. This is a simple one. Let's take P1 is one resource, P2 is a process, and P3 is another process. The resources are two types. There is a R1 resource. Okay, there is a R1 resource. 1 minute. There is a R1 resource with dot. One dot means one instance. One instance means if R1 is a printer, मतलब एक ही printer है, one printer is there. Okay, so there is a R2 resource which has two instances. Means R2 एक resource है जो कि दो है. Suppose R2 is a scanner and there are two scanners are present in this whole system or connected in this system, and the whole thing will be considered as your system. And how many processes? The number of processes are 3. The number of resources R1, R2, and one more resource is called as R3. Okay, then what he does, he is saying the P1 is requesting for R1 and R1 is held by P2 and this R2 is held by this and this R2 is held by this one. and now P2 is requesting for R3 and R3 is held by this P3. Let's assume like this. Okay, this is the scenario. Now, is there any cycle exist? Is there any cycle exist? Each one you consider. This is one vertex, this is one vertex, this is one vertex, and definitely P1, P2, P3 are vertex. Is there any cycle exist? Quick.
No, sir.
No. Why? Because in this case it is started here, started here, started here, it is not coming and it is completely free. Now guaranteed there is no deadlock because there is no cycle exist here. Why? Just look into it. Because who will, can you tell me in this scenario who will execute first? Complete its execution first. I have not explained, still I am asking. Is it P3? Is there any possible this P2 can finish its work? Not. Why? Because P2 demands R1, R2 and R3. Among these three resources, 2 has already allocated to P2, but R3 has not allocated. Why? Because R3 is of one instance and the same R3 is currently held by P3. So what happens now? So, and P1 cannot execute because P1 is demanding for R1, which is currently held by P2. Means P1 is depending upon P2, P2 is depending upon P3, but P3 is not depending upon anybody. Why? Because P3 needs R3 and currently he has R3. Since he has R3, what he does? He simply take this, use it, then release this one. The moment you will release, then what will happen? This is become free. If it is become free, then this resource will be allocated. Now, if it is becoming allocated, now P2 has a R1, R2 and R3. All three resources he got it. Once he got all three resources, what he has to do? He can do his work because he requests for three resources. Currently he got it, then he can do it. Once he finish this, then this is free, this is free, this is free. Now what is left? P1 is demanding for R1, which is currently free because P2 was previously hold this R1. Now it is become free, means now this is also allocated. Once it is allocated, R1 is allocated to P1 and already R2 has allocated to P1, means both the resources will be allocated, he can execute. Then what is the sequence of execution? The sequence of execution, here it is basically what? P3, P2 and P1. Sometimes they are asking the question, not in very simple way, but in another way. Okay, this is understood. Is it clear? Since there is no cycle, no deadlock. But we have to calculate it. Cycle is there, but whether there is a deadlock or not. So let's look into carefully. Suppose there is a P1, same P2, same P3. This is P3 and this is the same R1 and this is the same R2. This is held by this, this is held by this, this is held by this, this is held by this is become R3, one instance requested by this and held by this. And let's check, he is requesting for this. Yes. Now, can anybody tell me, is there any deadlock here or not? Is there any deadlock here or not?
Sir, there is deadlock.
There is a deadlock. Anybody else? First, what is the rule? The rule is you have to find out whether there is a cycle or not. That is the first criteria. You have to identify that whether there is a cycle exists or not. So if you can look into it, see this P1 demanding for R1 and R2. R2 has already held by P1, but this R1 is currently held by P2, and P2 requires R1, R3, R1, R2 and R3, but R3 is held by this P3, which is requested by P2, and this P3 is held by this requested to R2. So if you can look into it, this makes one cycle. Yes or no? This makes a cycle basically. Since it is a cycle, then he cannot release. Why? Because he wants R2, then only he can release this R3. But R2 को पाने के लिए P2 को चाहिए क्या है? This is in this one. That's why it is also in deadlock. Then what happens here? Here it is happen. If you can draw a figure, P1, R1, R2, and P2, then R3, then P3. So they are making like this one, yes, then this one, then this one, then this one. So if you can look at here, then there is a cycle. Since there is a cycle, so there is a chances of deadlock, and here exactly there is a deadlock. Then you can say, sir, you are telling like this, then which scenario there is a cycle but there is no deadlock? Just look into it. If I add one more instance here, is there any issue? There is no deadlock. Why? Because already one resource become free. It looks like a cycle, but there is no deadlock because this resource is currently free. Since it is free, this resource can be allocated to P3. Once the P3 get this R2, already he has a R3, he can release this R3. Once the R3 gets released, it will be occupied by P2, and the P2 will be get R1, R2, R3, then he will release this R1. Once the R1 gets released, the same R1 will be get by P1, and P1 will be get. So that's why they are saying, even if there is a cycle, you cannot give this guarantee that there is a deadlock. Then somebody will ask immediately, sir, how can you identify a cycle? Because finding a cycle for 4 nodes, it is quite easy. But if it is a big graph, how you can identify there is a cycle exists or not? So let's look into it. Suppose there is a resource called as nodes are P1, P2, P3, then P4, then P5, then P6, then P7, then P8, and then P9. Okay, these are the vertices. Okay, in a graph, and I'll make some particular edge. Yes. Okay, this, and let's assume that this is this, and this one is not a little. I'm removing this. I'm removing this. I'll make it as this edge. Then he has this, and he has this, and he has this, then he has this, and this much, and I assume that he has also this. Okay, this is a graph. If I ask you, can you find a cycle? It is not so easy by quickly seeing. And if it is in exam also, you will be more tense. Sir, होगा कि नहीं, पता नहीं चल रहा है कहाँ पर cycle. Then what is the way? The way is very simple. Is if any nodes are point to be cycle, these 3 nodes are in cycle when if every node has a incoming edge and outgoing edge. Yes or no? If there is only incoming, can you say that there is a cycle? Cannot. Yes or no? If I say if any vertex is present which has only incoming edges, can it will ever participate in cycle? Suppose a vertex has only incoming edge, so it cannot be. So because if you consider this, then he is participating in cycle because he has an incoming and outgoing. But if I draw like this a graph, if everybody is coming towards this and like this, then it cannot be a cycle. Why? Because this particular node is not participated in cycle. The reason, he has only incomings, but there is no outgoings. But for a cycle, I need something incoming, something outgoing, something incoming, something outgoing. And what next? What you have to do here, whether there is a cycle here or not, you first find out which node has only incoming address. So this node has incoming address, then what you can say? You can immediately say, sir, I can directly remove this edge and this edge. Why? Because after he get this resources, he can able to release it. Once you will release it, then this has only incoming edges, then it is also removed. Then no edges present means there is no cycle. But in this case, look into it. Can you remove this edges? No, because he has incoming, outgoing. He has incoming, outgoing. He has incoming, outgoing. Means we cannot remove it. Similarly, since it is a graph, how we can identify that which processes are in deadlock? Let's assume like this. And incoming usually says that I am now using that resource. Incoming usually we discuss here, if anything is towards me, means I am using this resource. So that's why if you can look into it, this P2 has only incoming. Then what I'll do? I'll immediately remove this, remove this, remove this. Now you again verify. Is there only incoming present here? Is there any incoming, only incoming present here? No. Because if you can look into it, this has incoming, outgoing. This has incoming, outgoing. And this has also incoming and outgoing. This process has incoming, incoming, outgoing, incoming. So you cannot. Now look into it. This has incoming, outgoing. This has incoming, outgoing. This has incoming, outgoing. And this has also incoming, outgoing. Means this processes, so they're guaranteed a cycle. Because if there is no cycle, means you can assume that no edges will be present after you apply this rule. What is the rule? Wherever you are finding only incoming, you remove these edges. So once the edges are free, then you have to look into it. Is there anything present? No, sir. Is there anything present? No, sir. He is requesting for somebody something, but he is not getting. Similarly, is there anything is present here? It is incoming, it is outgoing, incoming, incoming, and outgoing. So they are guaranteed a cycle. And if you can look into it, there is a easy cycles are present. So what is the cycle? Can anybody tell me what is the cycle here?
P6 to P5, P9, P3, P8.
Am I correct?
Yes, sir.
In this way?
Yes
or no? This is becoming a cycle. Yes or no? And this is also becoming a cycle. Yes or no? There are many cycles are present here. Since there is a cycle, then there cannot. So let's say, sir, आप बोले कि ये तीनों ही निकल रहा है, आप कैसे बोल दिए कि ये नहीं है? Suppose और एक डायग्राम बनाता हूँ, तो easily you can identify P1, P2, P3, then P4, then P5, then P6, then P7, then P8. Then you have to identify who are in the deadlock, who are not. Let's take it is coming here, this is coming here, this is going here, this is coming here, and this is actually coming here, here, and this is coming, this is incoming, and this one is outgoing, this one is incoming, this one is coming here, this one is incoming, then this is then this one is this. So let's take this is become incoming, and this is joining with this one, this is joining with this one. Okay, let's take this the graph. So how easily you can identify is that any cycle or not? So you have to first identify anybody has only incoming. This is incoming, तो क्या किया? इसको मिटा दिया, देखिए इसको मिटा दिया, फिर इसको मिटा दिया, फिर इसको मिटा दिया. Then is there only incoming? Anybody present? This is a incoming, so इसको भी मिटा दिया, इसको भी मिटा दिया, इसको भी मिटा दिया, इसको भी मिटा दिया. Is there any other S? This is also incoming, only incoming now. So इसको भी मिटा दिया, इसको भी मिटा दिया. Then is there only incoming? Sir ये भी देखिए incoming only है. So इसको भी मिटा दिया, इसको भी मिटा दिया. Then is there any incoming? Yes sir, this is only incoming. देखिए. So there was no cycle there. Even if it looks like a tedious graph, but if you apply this rule, you can easily identify that there is no cycle. Okay, so what is the simplest way you have studied? We just apply, first you search a node which is only incoming, and those all the edges connected, incoming edges connected to that vertex, you remove it. So after you remove it, definitely you get it. Yes, so this is the way to identify. So what you have studied? We studied the condition, 4 conditions. That is remember please, what are the 4 conditions? Mutual exclusion, hold and wait, no preemption, and circular net. If those 4 conditions satisfied, then only there is a deadlock. Then we studied how to identify a deadlock once you know that these conditions may be there. So to identify the deadlock, we have to prepare a resource allocation graph. And the resource allocation graph has a vertices, which is nothing but a process as well as the resource, and edges are the direct edges, and those direct edges are requested or assigned edges. Requested means the P1 is directed towards R1, that is a requested. If edge is from the R1 to P1, then it is assigned edge. And once you create a graph with this P1 process and the resource and edges, then you have to identify, is there any cycle exist? If there is a cycle exist, there may be a deadlock. If there is no cycle exist, that cannot be a deadlock. Like in this graph, the cycle exists, so there is a deadlock. In this graph, there is no cycle exist, means there is no deadlock. That is the approach. Now the question comes, I identified these things, that whether there is a deadlock or not. If there is a deadlock, or before the deadlock, how can you handle it? Because if a deadlock will occur, I cannot do anything with these processes. What I can do, sometimes I have to kill them. Suppose एक ऐसे हो रहा है कि 5 आदमी मिला के फाइटिंग, वो उसको मार रहा है, वो भी उसको मार रहा है, ऐसे मार रहे हैं. So if that is the scenario, what I'll do, there may be something will be available where I have to think about how to handle that situation. So to handle this situation like a deadlock, there are many scenarios comes into picture. One will say, sir, already fighting start ho gaya hai, you have to handle it. Or the another situation you can say that, sir, partially वो लोग किसी को मार रहे हैं, आप वहां पर चले जाइए, उनको थोड़ा जो मारपीट हो रहे हैं, कुछ आदमी को बंद कर दीजिए, सो अदर भाग जाएंगे. अगर पुलिस आ गया, दो आदमी, बस 5 आदमी थे, and two persons have started fighting, then if the police immediately comes, that somehow this deadlock will be avoided. Otherwise, what happens? If all 5 persons will start fighting, then police cannot control also. That will be a deadlock. Or another scenario may comes into picture. Sir, I know this area is a fighting area. So why don't you, from one day before, like before the election, one day before the election, why don't you bring the policemen and make them present there one day before? So this is another scenario. So they're saying, if there is a chances of deadlock or the deadlock has already occurred, then how to handle this deadlock? So the deadlock can be handled in 4 ways. So handling the deadlock. Very important, this one. Right? So inside the handling the deadlock, there are 4 scenarios. One is called the deadlock prevention. Then deadlock avoidance. The third one is called as the deadlock detection. Already partially we have studied just now with the help of resource allocation graph. Deadlock detection. and another one is called as the deadlock recovery. I'll give a hint like this, and basically our midterm topic is only deadlock prevention. Okay, but deadlock detection, some part will become like how to use this resource allocation graph. Yes, please ask.
वो लास्ट में क्या है वो डेडलॉक
sorry double, that is deadlock recovery. Okay, so what is this? I'll give a hint. Here the people are confusing basically in between these two. What is a prevention and what is the avoidance? Detection and recovery, somehow it is understood. Detection means some 5 people are there, somebody will go and identify that whether really they are fighting with each other and a deadlock has already occurred or not, or they are just fighting, normally fighting. अगर आप चिल्ला लोगे वो बंद कर देंगे, so वहां पर deadlock नहीं हुआ है. Yes, so that is called as a detection. You are identifying whether the deadlock has occurred or not. If it has occurred, then I have to recover from that scenario. Suppose fighting हो गया है, then what you have to do? So police क्या करेगा? What is the scenario of the police? So police क्या करेगा कि those who are fighting एक एक करके मारेगा. एक को मार दिया, एक आदमी को मार दिया वहां पर पुलिस जाके, सो और सब दौड़ के भाग जाएंगे. एक सिनेरियो भी ऐसे हो सकता है. मतलब क्या है, if 5 processes are in deadlock, एक प्रोसेस को मार दीजिए. Like in this scenario, if we can go for this, if P2, P3 are in deadlock, they are now creating a particular cycle which will make a deadlock. And what will do? पुलिस गया, इसको पूरा मार दिया. मतलब क्या है, this resources will be automatically free. If this resources will be automatically free, there is no question of deadlock. ऐसे भी हो सकता है. ऐसा no, that is one scenario. Another scenario क्या, what can be done? We will study in later. You can say, why don't you forcibly taken these resources from here? मतलब P3 के पास है, because of P2 and P3, this is in deadlock. Then why don't you take these resources forcibly from him? इसको बोले है आप नहीं रखोगे, इसको छोड़ दीजिए, अगर नहीं छोड़ता भी उससे ले लीजिए. So if you can take these resources forcibly from P3 and give it to P2, then P2 आराम से काम करके छोड़ देगा, उसके बाद P3 execute करेगा. So these are the scenarios or not? So that is comes under the recovery. So recovery requires a detection. Once you are detected that there is a deadlock, then you go for the recovery. But what is the prevention and what is the avoidance? The prevention says that like your corona preventive measure you are taking. Preventive measure मतलब पहले से ही आप कुछ वैक्सीन ले रहे हैं so that कोरोना होने का chances ही नहीं. That you can tell that. But what is an avoidance then? The avoidance and prevention is that before happening this event, you are taking the preventive measure. Means before this situation is going to be created, you have taken the preventive measure. मतलब पुलिस को पहले से ही लेके इलेक्शन बूथ में लेके एक दिन से पहले ही खड़ा कर दी. मतलब there is no question of a deadlock. जैसे हम लोग पे पोलियो टीका वगैरह देते हैं ना, yes, so that is a preventive measures. पहले से ही आप दे रहे हैं so that नहीं होगा. But what is the avoidance? Avoidance means already something has started, and time to time you verify whether I will be in deadlock or not. I will be in deadlock or not. Means dynamically you have to do something and avoid these things. But it is a confusing. मैं बस बोल दिया हूँ definition dynamically. But what is this dynamically? एक simple सा आपको example बता रहा हूँ. Suppose your department is computer science. Yes, yours also. And you have invited a hacker. Okay. So who will teach you how to make hacking? Yes. Then what you can do? So there, if the hacker will come to your department, then he may also create a disturbance. But you want to learn. You want to learn from this particular hacker. Then what is the preventive measure and what is the avoidance there? If hacker is going to create a problem inside your department, but you want to invite, the preventive measure is that remove all kind of electronics part inside your department.
दैट इज द फर्स्ट प्रिवेंटिव मेजर। ऐसा ना, अगर कोई कंप्यूटर होगा तभी जाके वो बैठ के कुछ करेगा ना, नहीं तो क्या करेगा? He will bring his own computer, sit there, then what is? Nothing is going to happen. Then what is the preventive then? The preventive measure is that before the hacker come to your department to give a talk, you remove all kinds of computer or gadgets from your department. Then there is no question of a deadlock or no question of a problem occur, even if this hacker will come to your department. But another one is avoidance. The avoidance I told dynamically. What does it mean? Suppose when you invite this hacker now, he told that I need few things. When I'll go to your department, please provide me few things. What? He told you, give me a keyboard and give me a monitor, and then you give me one CPU. Yes, he asks you these many things, and which is connected with the internet. This CPU is connected with the internet. He previously demanded these things. Please give me this keyboard and one monitor, one CPU. Yes, before you bring that person to your department, then what happens? The day when he is coming, you cannot previously say that no, hum log nahi de payenge. If you can't say like this, he will immediately say that fir main nahi jaunga. Then what the preventive measure says that if you take a preventive measure like this, that I cannot give you this key or keyboard or monitor or CPU, then he may not come also. The hacker may not come. But hacker says that you give me keyboard, monitor, CPU, when I'll reach to your department, then I'll go and talk. आप बोले कि हाँ ठीक है आप आ जाइए, there is no issue at all. We will provide you these things. The moment he comes, you cannot say, because he is a big person, you cannot say no. He first asks the keyboard. Then you maybe a doubt, sir keyboard मांग रहा है, कुछ करेगा क्या? नहीं, because he has his own laptop and he asks for a keyboard. आप बोले कुछ नहीं होगा. He is just fixing the keyboard with his laptop. Might be he is not comfortable with the laptop's keyboard. That's why he is asking for this. Because even if you give the keyboard, there is no problem affected to our department. एक रूम विजिट किया, नेक्स्ट रूम में क्या कि मुझे एक मॉनिटर चाहिए, बोल अब मॉनिटर फिर से मांग रहा है, सर क्या कर लेगा फिर? हाँ मॉनिटर दे दीजिए, बिकॉज यू आर सो ब्रिलियंट दैट यू डिसाइडेड मॉनिटर, एक सब स्टाफ को बुलाए, बोले कि मॉनिटर उनको दे दीजिए, बिकॉज यू डिसाइडेड इन योर माइंड इफ यू टेक द मॉनिटर व्हेदर ही विल क्रिएट एनी डिस्टर्बेंस. आप माइंड में अप्लाई किए, सर कुछ नहीं कर पाएगा. क्यों? उसके पास उसका लैपटॉप है, कीबोर्ड लिया, छोटा सा लैपटॉप है, वो देख नहीं पा रहा है, इसलिए बोल रहा है कि बड़ा एक मॉनिटर दीजिए, वो काम करेगा. सर मॉनिटर देने से, कीबोर्ड देने से अभी कुछ नहीं कर पाएगा. देन थर्ड रूम विजिट किया, उस टाइम पे वो मांग रहा है, सर मुझे सीपीयू एक दीजिए, मैं बोला था आपको 3 चीज देने के लिए, आप 2 मुझे दे दिए, फिर मुझे एक सीपीयू दीजिए. देन यू थॉट, सर इफ आई गिव दिस सीपीयू, देन मॉनिटर मिल गया, सीपीयू मिल गया, कीबोर्ड मिल गया, एंड सीपीयू के साथ इंटरनेट कनेक्टेड है, देन सर कुछ कर लेगा. Then that time you don't give the CPU. You just tell that, sir CPU थोड़ा बाद में, अभी कोई यूज कर रहा है, बाद में देंगे. Then you avoid that situation. That is called as the avoidance. Are you getting my point? From the very beginning, you don't tell that I will not give. If from the very beginning you tell that I cannot give, then somehow you are doing some preventive measures. But वो तो बड़ा आदमी है, वो आएगा ही, आपको पूछेगा मुझे कीबोर्ड दीजिए, मॉनिटर दीजिए. सो कीबोर्ड मॉनिटर तक आप दे पाए, बट द मोमेंट ही आस्क्स फॉर द सीपीयू, यू ट्राई टू अवॉइड इट. आप छुप के सब को बोल रहे हो, ए उधर आप थोड़ा उधर चले जाइए, बाथरूम को चले जाइए, आप ऐसे बोल रहे हो, मींस यू आर अवॉइडिंग दैट सिनेरियो. Okay, so we'll study then what is this, how can you do the preventive. Then later we'll go after tomorrow's class, we'll go for the avoidance. But what is the preventive? The preventive measures will be, first think about because of what the deadlock occur. If those things will be somehow restricted, guaranteed preventive measure will be happening. Yes or no? because of what this coronavirus occurred, if those things will be somehow prevented, guaranteed the corona will be not there. So now we can think, in this case, the deadlock happened because of whom? Because of 4 conditions: mutual exclusion, hold and wait, no preemption, and circular wait. Then what is my preventive measure? The preventive measure is that don't allow, at least don't allow any one of them to be occur. मतलब मैं hold and wait को allow नहीं करूंगा करने के लिए, then that is a preventive measure. अगर hold and wait नहीं होगा, there is no deadlock. और नो प्रीएम्पशन को अलाउ नहीं करूंगा, मतलब सबको मैं बोल दूंगा कि आप प्रीएम्प्टिव हो, then there is no deadlock. Or there is mutual exclusion. Every device is connected to my machine is shareable. There is no question of a mutual exclusion. That is another scenario. Or I'll think about, I'll not allow to be circular wait. ऐसे cycle create ही नहीं करने दूंगा. Then there is no question. So what you have to study? We have to study in the deadlock prevention. How can you avoid mutual exclusion or no preemption or hold and wait or circular? अगर चारों से any one of them will be not occurred, means that preventive measure has already taken. So the next class, tomorrow's class, will study how you can do it for 10 minutes. We can complete this. Then we'll start this avoidance. Okay. So this is the case. Fine. So today is this much. I have one more class. I hope you understood this, because this is the easiest topic. You can quickly get the marks if the questions are coming. Yes, mostly the questions may come from here. Write down all the scenarios of the preventive. So we'll study 4 scenarios. How can you avoid, how you will not allow for the no preemption or circular wait or hold and wait or mutual exclusion, or they will give a graph and tell that in a short question, please identify whether the system is in deadlock or not, or what is a resource allocation graph, they may ask you, and what are the 4 conditions for deadlock, and what is the deadlock's definition. Maximum they can ask you this. Okay, latter part will be little difficult. It's okay? Understood?
Yes.
Yes, fine. Thank you.
Sir, please send the recording.
today आज मिलेगा तुरंत.
Okay.
Okay, thank you very much.